Welcome! Today we are exploring the Floyd-Warshall algorithm. While Dijkstra's algorithm often gets the spotlight for finding a single path, Floyd-Warshall is the heavy artillery of graph theory. It solves the all pairs shortest path problem, calculating the distance between every single node and every other node in the network. It is an elegant masterpiece of dynamic programming that runs in big O of v cubed time. To understand Floyd-Warshall, we must shift our perspective. Most introductory algorithms like Dijkstra or Bellman-Ford are single source. They tell you how to get from point A to everywhere else. But Floyd-Warshall gives us a complete distance metric. It characterizes the connectivity and interaction cost between every possible pair of vertices in the graph simultaneously. This algorithm is so fundamental that it was discovered independently by 3 different computer scientists around the same time. Bernard Roy found the recurrence in 1959, Robert Floyd applied it to shortest paths in 1962, and Stephen Warshall simultaneously used the same logic for transitive closure, simply checking if a path exists. This is why you might hear it called the Roy-Floyd-Warshall algorithm in rigorous circles. At the heart of the algorithm lies this beautiful recurrence relation. Here is the logic. To find the shortest path from I to j, we check if we can improve the current best path by taking a detour through an intermediate node k. Mathematically, we ask, is the path from I to k plus the path from k to j shorter than the direct path we already know? We repeat this question for every possible intermediate node in the graph. A naive dynamic programming approach might suggest we need 2 matrices, one for the previous state and one for the current state. However, Floyd-Warshall has a special property. During the kth iteration, the values in the kth row and the kth column do not change. This allows us to overwrite the matrix in place, reducing our space complexity from 2 times v squared down to just v squared. This is crucial for cache efficiency. The implementation is incredibly simple, consisting of just 4 lines of core logic. We have 3 nested loops. The outer loop iterates over k, the intermediate pivot. The inner loops iterate over the source, I, and destination, j. It is vital that k is the outermost loop. If you change this order, the dynamic programming dependency breaks, and you will get incorrect results. The complexity profile is deterministic. It runs in big O of v cubed time, regardless of whether the graph has 1 edge or a million edges. While this sounds slow compared to Dijkstra, the operations are simple array accesses with no complex data structures like priority queues. This makes Floyd-Warshall surprisingly fast for dense graphs, where the number of edges approaches v squared. This is where it gets fascinating. Floyd-Warshall is actually just matrix multiplication over a different algebraic structure called the Tropical Semiring. In standard algebra, we multiply and sum. In the tropical, or min plus semiring, we replace the sum operation with minimum and the product operation with addition. This algebraic isomorphism allows us to adapt the algorithm to solve many other problems. By simply swapping the operators, the same triple loop structure solves completely different problems. Use Boolean OR and you get transitive closure, finding who can reach whom. Use max and min, and you solve the widest path problem, finding the route with the maximum bandwidth bottleneck. It is the same code, just different math. Unlike Dijkstra, Floyd-Warshall handles negative edge weights gracefully. However, negative cycles are a trap. If a cycle exists where the total weight is negative, you can loop infinitely to reduce cost. The algorithm detects this if the distance from a node to itself, d sub ii, becomes negative. Without safeguards, these values can underflow integer limits, so robust implementations must check for this. For modern supercomputing, the basic loops are memory-bound. To fix this, we use tiling, breaking the matrix into small blocks that fit in the CPU cache. We can also use SIMD instructions to update 8 or 16 distances in a single clock cycle. On GPUs, we can parallelize the updates massively, making Floyd-Warshall incredibly fast for large-scale simulations. Calculating the distance is useful, but often we need the actual route. To do this, we maintain a secondary matrix called the predecessor matrix. Whenever we find a better path through K, we note that to get to J, we must come from the same node that precedes J on the path from K. We then reconstruct the full path by backtracking from the destination to the source. This algorithm powers the world around us. In software-defined networking, it calculates global routing tables for the internet. In hardware design, it optimizes the data flow inside multi-core processors. Biologists use it to analyze metabolic pathways, and chemists use it to compute topological indices that predict physical properties of molecules. So, when should you use it? If your graph is sparse, like a roadmap, run Dijkstra or Johnson's algorithm. But if your graph is dense, or if you need to handle negative weights, Floyd-Warshall is the winner. Its simple memory access patterns allow it to outperform Dijkstra on modern hardware due to superior cache locality and vectorization potential.